So let's talk about some unique situations that can occur as we make more and more complex models with multiple regression. The first thing that we need to be aware of is the potential of a suppressor variable. Now, a lot of times students will talk to me and ask when we're talking about multiclinearity, when we're talking about residuals, when we're talking about suppressor variables, how will I know I have one? And the answer is not that clear. Suppressor variables and all of these issues are identified by certain conditions occurring, but even then, it may not necessarily mean you truly have a suppressor variable. So a suppressor variable correlates with other predictors, but is not directly related to the outcome. So that's the basic definition. But not all variables that are unrelated to the outcome are going to be suppressor variables. In order for a suppressor variable to be a problem is when it actually becomes significant in the model when it wasn't significant by itself. And what this is this is basically a statistical artifact or a mathematical artifact of the fact that as we create more and more complex models, we're having to decide, and by decide I mean the equations are deciding, where variance goes. And as you add more and more predictors and more variance is shared variance, there's going to be error, either positive or negative, in all of those predictions. And what can therefore occur is that if you have a predictor that is unrelated to your outcome, but is highly related to another predictor, it may actually eventually, through error and estimate, be assumed that it's actually sharing variance in the prediction of the outcome. So in this case, we have a very simple model. We have commitment, we have education, and we have years of marriage. Years of marriage is our outcome. Commitment is clearly related to years of marriage. Education is clearly related to commitment. So those with higher education are positively related and tend to have more commitment in their relationships, and those with more commitment in their relationships have more years of marriage. However, your level of education does not directly predict the years of marriage that you've had. So there is no direct relationship between the two. So if we were looking at the bivariate correlations, we would see a relatively strong relationship between education and commitment. We'd see a relatively strong relationship between commitment and years of marriage, and we would find no relationship between education and years of marriage. That's not a suppressor variable at this point. That's simply a variable that's statistically not significant. It doesn't need to be in the model. But what can occur is as we put that into a model, as the model gets more and more complex, its relationship with commitment may drag it into a relationship with years of marriage. And again, it's a little bit hard to visually conceptualize this, but just recognize that whenever we're drawing these Venn diagrams, they're estimates of variance. So we're estimating A, we're estimating D, we're estimating the remaining error or remaining variance in commitment, F, or education, F, or in years of marriage, E. And because those are estimates, there's plus and minus error in those estimates. As we create a more and more complex model, the goal of multiple regression is to account for as much variance as possible. So it is always going to side on the side of overestimating variance explained than underestimating. And that can effectively drag the orange circle and the pink circle onto each other as the model gets more and more complex. So suppressor variables do not directly correlate with the outcome in bivariate one-on-one correlations. Education is not related to years of marriage, R 0.02, non-significant. However, strong correlation with other predictors may make the suppressor appear, and by appear, I mean it will turn out being significantly related in a complex model to our outcome. So education is result related bivariately, so just the two of them, to commitment, an R of 0.5, significance of P equals 0.01, and commitment is related to years of marriage, R of 0.65, P again below 0.01. A regression that includes both these predictors may suggest they're both significant. So what does this really mean? This does mean that there's a reason we run a correlation matrix of bivariate correlations before we run any multiple regression. It gives us a quick snapshot. It doesn't give us the whole picture, but it gives us a snapshot. And we can also take a look which of our predictors were bivariately related to our outcome. And if we have one that is not related in the bivariate correlations, but then in a more complex model shows up as related, we want to ask the question, is it a suppressor variable? And the way we'd identify it is we'd go, is it strongly related to other predictors that are related to our outcome and only becomes related to our outcome in a complex model? That is an indicator of a suppressor. We probably need to remove it and identify it in our methods or our results section as here's why we identified it as a suppressor variable and here's why we removed it. And the problem of this is the reason is if we included it in that model, one, it's probably just stealing the variance that it's explaining from another predictor. And two, it actually isn't a relevant predictor to begin with. So we're basically being tricked by an advanced model into giving credit to a predictor that should not get credit in predicting our outcome. The next thing we need to look at is multiclinearity, or sometimes just referred to as collinearity. It occurs when two or more predictor variables are highly correlated. Now this is different than suppressor variables because with multiclinearity, both of the predictors are related to the outcome. The problem here is that they're so related to each other, it makes it difficult to determine which predictor has an effect on the outcome, and can also cause some pretty large shifts from model to model if we're doing hierarchical regression. In other words, we're testing multiple models with more and more complex models. We may actually find that in some of the models, it makes sense mathematically to give all the variance that's being explained by two predictors to one of those variables. However, in a later model, it may actually suggest that that predictor is no longer significant at all because it's now given the variance to the other predictor. Again, what we're doing here is we're losing power. Same with a suppressor variable. A suppressor variable, when it exists, isn't needed in the model, even if it's significant, because it's basically just stealing its significance from something else. Power is reduced with multiclinearity as well because basically we have two predictors that are basically just competing back and forth for that variance. One of them can do fine. A good example of this is emotional coping and alexithymia. Both of them are highly related to each other, and therefore if they were in the same predictive model, there's a good chance they might suffer from multiclinearity. Generally speaking, multiclinearity can be reduced by removing the redundant variables, but we should make sure that we're looking at both theory and statistical contributions. So theory, if you have two variables, two predictors that are suffering from multiclinearity, the first thing you can do is look at past theory, which one is actually more often found to be related to the outcome. That might indicate which one you should keep. If you don't have a strong theoretical reason, you could also go back again to those bivariate correlations in that correlation matrix at the beginning. Which one actually just is, to begin with, a stronger relationship between it and the outcome before we start using advanced models. The same thing can be done to some degree with suppressor variables, except the suppressor variables shouldn't be related at all by either theory or statistical contribution. So we're much cleaner once we've identified a suppressor variable, just removing that suppressor variable. When we identify multiclinearity, we need to decide which of the variables we want to remove, and that takes us to this theory versus statistical contribution as two different ways to decide which one should be removed. So here's an example, and again, you'll see that this is much different than suppressor variables. In this case, we have emotional coping, we have alexithymia, and we have alcohol abuse, and they're all highly correlated with each other. The problem here is that large section of B. B is a pretty huge chunk of alcohol abuse that's predicted equally by emotional coping and alexithymia. Since they're so highly related, depending on the models, we may see wildly shifting betas, B weights, and significance for emotional coping and alexithymia from model to model as each model decides in this particular complex model which variable does it make sense to give that variance of B to. So again, bivariate correlations, how do we identify a multiclinearity situation? The first thing we can do is just bivariate correlations. Highly correlated IVs typically indicate multiclinearity. A Pearson correlation of 0.9 or negative 0.9 or greater tends to be problematic. Now, I said tends to be. It may turn out that you have two predictors that are highly related, but they don't shift back and forth through models. They always pretty much stay stable, and they are predicting fairly similarly. In that case, what we'd have is they do share variance, but most of the variance shared is not in the prediction. It's between themselves. If we thought of the Venn diagram, there would actually be very little shared variance in the actual prediction. There would be a fair amount of unique prediction being done by the first variable and a fair amount of unique prediction being done by the second variable, and most of the overlap would be containing between the two variables. So this would be an example of where you have two variables that are highly correlated, but neither of them are predicting a lot of variance in the outcome, and the variance they are predicting is different variance. So just because you have, sorry about that, my phone just went off. Just because you have a high correlation between two predictors, it is very likely you're going to have an issue of multicollinearity, and you should either use theory or statistical strength to determine which one to remove. But don't immediately assume it. Do take a look and see how those two variables are performing at different levels of your model. There is another way to basically measure multicollinearity, and you can ask for this in most statistical packages, and that is variance inflation factor. It measures the influence that one or that the other IVs have on the standard error variance in a particular IV. So you have the IV that you're interested in, IVJ, and you're basically calculating how much variance in IVJ is actually being explained by all your other IVs. As more IVs correlate with IVJ, the IV that we're interested in, the harder it is to make predictors of the DV from IVJ. In other words, IVJ, the more it's related to other predictors, the more likely it is not going to be easy to identify what variance it actually is responsible for in your actual outcome or DV. So how we actually measure VIF is it should be close to 1, and it should certainly not exceed 5 or 10. And generally, again, different texts are going to argue on this, on when do you have to really worry about VIF factor. What I would suggest is that the closer your VIF is to 1, you're probably fairly confident that that isn't an issue of multicollinearity. If it exceeds 5, I would check the bivariate correlations between the various variables in the equation. Are any of them higher than 0.9 or negative 0.9? If so, you may want to remove that for multicollinearity. If you find that you have a VIF of 5 to 9, but you don't see those strong correlations, I think you probably are fine leaving in a predictor until VIF exceeds 10. Probably over 10, that's a good enough reason that there's just not enough variance that it's explaining the outcome to make it worth your time in the model. Now, most of the cases, you're going to see that with multicollinearity, you're not really getting a big advantage of having that predictor in the model anyway. So again, there isn't a single set answer to this problem, but there are multiple indicators we can do and look at, including how variance is changing or the strength of our predictors are changing from model to model. So calculating the variance inflation factor, it's a very simple equation once you've actually figured out all of the variance explained in J of the other predictors. So the kind of big mystery to this equation of creating a VIF factor is you do have to calculate how much variance is accounted for in the independent variable J by all other IVs. You take that R squared, that effect size, again between 0 and 100%, and run it through a simple equation, 1 divided 1 minus that percent. If the RJ is 0, then there's no relationship between the IV and the other IVs. It would be 1 over 1 minus 0. So 1 over 1 is 1. That's a VIF of 1, no relationship. Tolerance is the reciprocal of VIF, or 1 minus that R squared, so basically what's left of the variance. And again, you can kind of tell that the larger the variance, the less of tolerance there's going to be. So if basically your IVs are explaining 0.9%, so your R squared is 90% of variance is being explained in your IV by other IVs, that only leaves about 10% of tolerance. There's only 10% left in that variable that could even be involved in trying to predict the outcome. So again, it should be close to 1, and again, if your VIF actually ends up being closer to 0, in other words, if it's below 1, that can also be problematic, and that's usually involved in very complex models where the R squares are actually, there is more variance being explained in the outcome, or there's more variance being explained in that predictor than that predictor actually has variance. Now again, you ask, well, how could that happen? Remember that these mathematical equations are estimating variance, and they tend to estimate high. They tend to try to gather up as much variance explanation as possible. So if you have 7 IVs in one model all predicting something, and you're trying to calculate how much each of those IVs predicts in another IV, you may actually end up with something where the number is over 100%. And that's where you'd get a negative VIF, or a VIF approaching 0 instead of a VIF of 1 or greater. If that happens, that also tells you that you're probably actually getting close to overfitting a model, and we'll talk briefly about that in a moment. So with model selection, the process of model selection also is systematic, but should be driven by both statistical analysis and past theory. So each additional variable should be adding to the model. So each additional variable should be significant, and the other existing variables retain significance as you move forward. And model selection is generally being done with hierarchical regression, where we're choosing to enter variables in blocks. And again, outside of specific theory or specific hypotheses, our first block is going to have the individual predictors. We're going to let them actually explain variance in our outcome without any other additional relationships. If we think that there's a chance of nonlinear relationships, we may test those next. We then may test relationships that involve the various interactions. And again, depending on how complex you are, you may also go through a process of only adding 1 or 2 variables per block as you make more and more complex models. So each model is going to be defined by you based on which predictors or interaction predictors or various terms, nonlinear terms you've created that you put into each hierarchical level. For each level, we want to check the R-square, how much variance is being explained, and F, is that model significant? In this case, F is an omnibus test. And again, an omnibus test simply means an overall test of variance being systematic. We also want to look then, after that first model, at the R-squared change and the F change. In other words, are we gaining variance explained by adding to the model? And is the F getting larger? We want to see a positive, significant F change. In other words, we want to see our omnibus test of the model get larger, meaning there's more variance explained, and that increase in size is significant. It is statistically significant. It's not due to just a chance. It's a large enough change that we can be confident that whatever we did to move from block 1 to block 2, whatever variables we added, they significantly increased our ability to predict. And our ability to predict would be indicated by the R-squared change. How much percentage of variance are we now explaining compared to the last model? Once we've actually chosen the model that we're going to use, we then use t-tests to check each individual predictor to make sure it's significant. And again, this is where we'd be looking for potential suppressor variables and multiclinearity. Are the coefficients changing? Are the individual significant t-tests changing? This would generally indicate that particularly variables may be somewhat redundant. And the final issue we want to worry about is overfitting. Just as a reminder, whenever we're doing multiple regression, it's trying to find the very best fitting model. It is also generally skewing towards positive variance or positive error in its prediction. It's always trying to explain as much variance as it can with each subsequent model, which tends to mean that as we create more and more complex models, we start to get overfitting. We start to get a little bit of basically an inflation, if you will, of how much R-squared we're actually explaining in the outcome. As I already talked about with VIF factors, we can actually result in fairly complex models in situations where we're explaining more than 100% of variance in a variable mathematically, which of course in reality is not really possible. One of the ways that we can adjust for this is adjusted R-squared. So when you're looking at models, you'll be getting the unadjusted R-squared, but recognize that may overestimate the effect size. And this is because R-squares are never negative. So if we're actually calculating the overall impact or effect, all of our R-squares are always positive. They're always going to add up. And again, the estimation of error is always given towards a better fitting model. So all variability due to chance tends to inflate that R-square. So an adjusted R-square corrects for this and for sampling bias. The equation is over here. Basically, our adjusted R-square is 1 minus 1 minus the original R square multiplied by N, that's large N, total sample, minus 1, divided by large N minus the number of predictors, minus 1. This will make a slightly smaller R squared and typically is a much more accurate measure of how much variance that total complex model is measuring. Now again, if we have a predictor model with one predictor and one outcome, there is no need to create an adjusted R squared. R squared is going to be accurate. This is an occurrence that happens with more complex models with multiple predictors. So just a quick summary of multiple regression. R squared is the amount of variance in Y explained by the set of predictors, whichever model we choose. And the F test is whether that model total is statistically significant. It is an F test. It is an omnibus test. Our B is our regression coefficient, sometimes referred to B weight, but it is not a direct comparison of B weights. And what I mean by that is we can't compare B weights from one predictor to another because each predictor may be on a different scale. All the B weight refers to is the amount of change in Y predicted by one predictor or one nonlinear predictor or one interaction that we've created. It's independent of all other predictors. And once we have selected our best fitting model, we still want to conduct t-tests to make sure that each individual predictor in that model is actually a significant contributor. So again, B weights are not standardized. They're still on the measurement scale of each individual predictor or interaction predictor. That's why we also want betas, standardized B weights, and they are interpreted approximately like correlations. So they allow us to compare contributions predictors. The larger the beta, the more that particular predictor is actually explaining in the variance of our outcome.